Hello and welcome back to the lecture on business econometrics. In this lecture, we are going to touch upon a particular topic which people often confuse, and this is basically related to the two terms. One is independence, and the other is the mutually exclusive event. So, if two events are independent, whether they are mutually exclusive, or if two events are mutually exclusive, whether they are independent. So, I repeat again, if two events are independent, whether they're mutually exclusive, or if two events are mutually exclusive, whether they're independent. Now, these two terms actually appear pretty similar, and that is why people actually do confuse. But let me actually work on it a little bit so that I can, like show you in different way. So I will use first intuitive understanding, then I'll use an empirical example, and then finally I'll do some mathematical illustration to kind of tell that um, mutually exclusive does not imply independence. Mutual exclusiveness does not imply independence. In fact, the opposite. So let me first write down what do we mean by mutual exclusive and independence. So by independence we mean occurrence of one event occurrence of one event does not influence the occurrence of the other event, whereas mutual exclusive means mutual exclusive means the occurrence of one event implies non-occurrence of the other. Occurrence of one event implies non-occurrence of the other event right? So occurrence of one event implies non-occurrence of the other event. Now look at these two definitions pretty carefully. So one is that occurrence of one event, independence, has nothing to do with the occurrence of the other event. X has nothing, the occurrence of X has nothing to do with the occurrence of Y. Whereas for mutual exclusive, if the events are mutually exclusive, then that means the occurrence of X means Y is not there. Non-occurrence of Y is out, right? So that means the moment X comes in, if they're independent, X has nothing to do with Y. Y may come, Y may not come, X doesn't care. On the other hand, for mutual exclusive, if X is coming, that means Y is not there. So that means there is an element of dependence when I'm talking about mutual exclusiveness, that the moment X comes in, Y goes out. So it means the existence of Y is dependent on the existence of X. So that's the intuitive understanding that mutual exclusiveness does not imply independence. Now I will actually show you an example to kind of prove what I just said. This is an empirical example. So this is a second way of illustrating it. The example goes like this. Suppose I throw a fair coin. So let me use a different color. Um, Throw a coin and I actually roll a dice. Okay, throw a coin, roll a dice. And I want to know. So let's say I have my event A is getting a head, and event B, say, getting a 6. Now I want to know the probability of A and B happening. So probability of A union B. Now these events are independent because coin tossing has nothing to do with dice throwing. So let me write down probability of A union B is, sorry, A intersection B is probability of A into probability of B. So which means basically probability of A is half and this is 1/6. So that is 1/12, right? 1/12. Now if they're mutually exclusive, if these events are mutually exclusive, if mutually exclusive, by definition by definition, there is no common element, right? Probability of is equal to 0, right? So it is not equal to this. So this is not equal to this. So this means what I said, that mutually exclusiveness does not imply independence, right? So they are not equal. Now there is another way of explaining it, and that is basically by mathematical way of illustrating it. So let me write down another example. Example 2. Example 2. The initial one was example 1. This is example 2. And in this example 2, I'll sort of show, say, let's say I have two events A and B. I have two events A and B. All right. Event A, event B. And I have drawn in a way that they're mutually exclusive. There is no common element between them, so they're disjoint. So mutually exclusive also means disjoint. Okay. And so when A and B are disjoint, so probability of A union B, we know, is equal to probability of A plus probability of B minus probability of A intersection B, right? Now we know that for mutually exclusive event, this is simply 0, right? There is no probability of A intersection B. In other way, we can also say that, since there is no common element here, so we can simply write A intersection B gives me a null set, and when I do a probability, when I take a probability of this, it is basically 0. So either way, I can say that probability of A intersection B is equal to 0, right? If they are mutually exclusive. Now, but in any case, whenever I take a probability of A, this is an event probability of A, and it is occurring here. So it is basically, it has some value greater than 0, and I have probability B, which has some value greater than 0, right? Now, if they're both mutually exclusive as well as independent, if if it's both, if say two events, if they're both mutually exclusive and independent, then what will happen here is I will have probability of A intersection B has to be probability of A into probability of B, because that is what the rule of independence is. Now I know that probability of A union B, it is A intersection B is equal to 0, because they are mutually exclusive, and I know my probability of A is greater than 0 and my probability of B is greater than 0, right? So that means my left side can never be equal to my right side, right? So that is basically, this equality does not hold. So that means, so mutually exclusive, mutually exclusive events does not imply does not imply independence. In fact, they are dependent, right? They does not imply independence. In fact, their dependence. So that's basically one confusion we often have, and that's what we wanted to clarify in this lecture.